So Steve will
Okay, great.
talk about the studies of quantum disorder on J-effective one-half triangular lattices. So over to you, Steve.
Okay, great. Yeah, thank you very much for the introduction, and thanks for the organizers for the opportunity to present some of our research at this conference. My apologies that I couldn't be there in person. I was looking forward to coming, but yeah, unfortunately, I had some other things intervene. So yeah, I mean, so as the chairman mentioned, the title of my talk is Studies of Quantum Disorder on J-effective one-half triangular lattices, and it's going to sort of be an experimental talk to try and motivate at least our interest in exploring a series of two different classes of triangular lattice magnets, of antiferromagnets, that we think host rather interesting sort of quantum disordered ground states that we've been working on in recent years trying to understand more about. And so sort of just an overview of what I'll be talking about is I'll just start with a very brief introduction, perhaps for any graduate students in the audience, and then talk about first a series of triangular lattice antiferromagnets that are built from S-effective one-half rare earth ions. Basically in sort of, the ground state, you have sort of S-effective spin orbit entangled wave functions. And then the second class will be more of a sort of what I call sort of J-effective one-half triangular lattice built from a transition metal ion, so a ruthenium ion, in particular sodium ruthenium O2. And so that's some of our recent work. And so, yeah, so let me go ahead and get started. So first off, just as a quick overview, obviously triangular lattice antiferromagnets are sort of the seminal, or I guess the canonical platform for trying to understand frustrated magnetism and trying to explore what types of new magnetic ground states one can realize due to magnetic frustration. And we know sort of in the sort of Heisenberg limit, even sort of in the quantum Heisenberg limit, that a triangular lattice should form this sort of so-called 120-degree antiferromagnetic ground state. And this has instabilities, of course. As you apply a magnetic field, you can transition from this 120-degree ground state into sort of this collinear, so-called up-up-down state as a function of magnetic field, into a series of other sort of V states and other types of magnetic instabilities. And also, as you tune magnetic anisotropy and sort of, for instance, exchange anisotropy, it's well known that you can generate quite a diversity of different types of magnetic spin states. For instance, looking at incommensurate spirals or spin density wave states, right? This is some work from Leon Bluelance's group. So in trying to stabilize quantum disorder on the triangular lattice antiferromagnet, at least our perspective, has been looking at sort of these sort of a lot of theoretical work in terms of trying to engineer anisotropy and to trying to destabilize the long-range magnetic order. For instance, going back and trying to engineer like purely Ising moments, or to try and engineer bond-dependent exchange terms. So for our perspective, has been basically to try and realize some of this is to try and encode some types of orbital component to the magnetic moment. And so having the orbital component not be lifted via like trivial electron phonon coupling, by having the lattice itself trying to lift this orbital degeneracy, one way of doing that is to try and decorate a triangular lattice with a sort of a spin orbit entangled wave function. So use a spin orbit coupling to try and encode these sort of anisotropies. And so we've been looking at this sort of experimentally in sort of two different limits. One is the limit in which spin orbit coupling is strong compared to the crystal electric field. And the second is the limit in which spin orbit coupling is relatively weak compared to the crystal electric field. And so I'll talk about these sort of some of our recent results in looking at these two different limits in a series of materials next. So first, I want to talk about some of our work looking at triangular lattice antiferromagnets built with these sort of so-called S-effective one-half wave functions where the spin orbit coupling is strong relative to the crystal field. And this is just for the grad students, a quick review. So when you use rare earth ions as your magnetic ion, for instance, here's an example for a ytterbium-3+, so single hole, versus cerium-3+, a single electron case. If you were to put this rare earth ion in sort of a low symmetry crystal field, basically distorted cubic crystal field, then we know that these two Kramer's ions are going to basically be split, but you'll always have sort of Kramer's degeneracy, so they'll split into a series of doublets. And so the idea is that if the splitting is large enough, for instance, tens of million electron volts between the ground state doublet and the first excited state doublet, as you cool down towards low temperatures, at temperatures where the magnetic exchange between these rare earth ions is relatively weak, so basically at temperatures where that exchange is relevant, then you've more or less condensed into this sort of ground state doublet, and these higher excited doublets are not populated. And so this sort of, you kind of cool into this S effective 1/2 ground state. And this is the same for the two. And so these are the two limits that are sort of what we've been looking at in terms of looking at, using rare earth ions in a triangular lattice antiferromagnets. And a lot of the sort of seminal work in trying to look at this was done on this material ytterbium, magnesium, gallium 04, which was about 7 years ago now for some of the initial reports. And this system is interesting. Basically it's a triangular lattice of ytterbium ions, again in sort of this reasonably distorted oxygen octahedra. And so in this system in particular, there's no magnetic order observed down to above 50 millikelvin. And when people did the sort of inelastic neutron scattering measurements, one can see that there's sort of continuum dynamics suggestive of a quantum disordered ground state. And so we sort of got interested in these triangular lattices of ytterbium ions when these results came out. And sort of one of the issues with this initial material was that there's substantial charge disorder between the layers, meaning the magnesium and the gallium sort of share a site. So you have sort of maximal alloy disorder in this material, which can lead to charge disorder. And perhaps, it influences the crystal field environments and perhaps influences the magnetic ground state. So a system that we looked at initially was the sodium ytterbium O2, which is sort of this Della-Fossite-like structure, where again, you have triangular lattice planes of ytterbium ions separated now by alkali metal spacers in terms of the sodium ions. And this system, actually, so the sodium and oxygen sites are fully occupied, so it's a stoichiometric system. And what we found is that basically this system, similar to the ytterbium magnesium gallium 04, doesn't order down to 50 millikelvin. And this system actually also we discovered sort of has a very interesting instability, meaning that when you apply a magnetic field to the system, you can actually drive it from this quantum disordered state into sort of a field stabilized, this up-up-down collinear instability. And so one of sort of the more striking things is if you look at the inelastic neutron scattering data, so this is looking at basically this is energy transfer versus momentum transfer, and then the color scale is basically the scattering intensity. One can see that under zero field, you just have a broad continuum of inelastic, basically of spin fluctuations, which are sort of centered about the sort of 2D magnetic zone center, about this sort of 120-degree zone center. And as you apply magnetic field, what you find is that the spectral weight more or less condenses into a Bragg peak, which corresponds to the sort of up-down state, as well as sort of this well-defined sort of these branches of spin waves, which we can model, which Leon Bulentz can model, which I'll show you in the next slide, is sort of a slightly XY anisotropy sort of Heisenberg model. Okay. And so just as a quick overview of the types of interactions that are allowed in the system, basically, this is from Leon Bulentz and Chungju Liu's work. One can decompose the terms into sort of, an XXZ term, these sort of compass-like terms which encode anisotropies, as well as interlayer XXZ and compass terms. And so if you just take the simplest case, which is the 2D classical phase diagram for the XXZ model, then the sort of field-driven instability can be captured into sort of what they call this sort of canted phase, which is more or less an up-up-down phase with a slight cant along the collinear moments along Z, which we can't completely rule out from our refinement of the spin structure, but certainly this model also doesn't capture other interactions like quantum fluctuations and other types of exchange terms, which might actually stabilize a purely collinear state. So just showing you what happens sort of in the static channel for sodium ytterbium O2. If you just look at the susceptibility, of course, then as you ramp magnetic field, you see the susceptibility suppressed. You cross this phase boundary and you enter sort of around 3 Tesla, this sort of collinear up-up-down state, which we can capture via neutron diffraction measurements, and we can model it as this collinear spin structure shown here. Okay, so this is just more of a detail of what's actually happening in the elastic channel as you saw that inelastic spectral weight sort of condense into the Bragg peak under magnetic field. And so this ends up being sort of quite an interesting example of this triangular lattice system with kind of intrinsic quantum disorder that can be driven with fairly low magnetic fields into sort of a fluctuation stabilized ordered state. Okay, and so here's sort of how the phase diagram shakes out for the system, from our powder work on the sodium ytterbium oxide, where again, at low temperatures and low fields, you have sort of what seems to be a quantum disorder, a quantum spin liquid-like state that you can cross a phase boundary around 3 Tesla into this up-up-down state. And then we have some additional work that shows that this sort of the high field phase boundary seems to have some first order character to it into a non-collinear state upon basically sweeping the field down. And this type of phase diagrams actually matches very nice, some beautiful NMR work shown here, showing a kind of a qualitatively similar phase diagram for the same system, where again, they sort of capture a series of different magnetic states at this high field phase boundary. And it's also reminiscent of some earlier numerical cluster mean field studies of a triangular lattice under magnetic field, basically where there's predicted to be sort of a first order transition to this V state. Okay. So what's sort of exciting about these systems is, that there's sort of somewhat similar behavior has been observed across many different classes of these ytterbium-based triangular lattice materials. For instance, changing out the alkali metal site from sodium to potassium to cesium, for instance, or changing out the anion site from oxygen to sulfur to selenium. Across this rather large class of compounds, sort of qualitatively similar behavior in terms of sort of an intrinsic disordered state and a field-driven instability has been reported. I will mention that some of these, there are some additional details though that like some of these seem to form quasi-two-dimensional order in the ground state rather than sort of a purely disordered state. For instance, like you can kind of see this broadish hump and the susceptibility here of the cesium compound. There's reports, for instance, of the potassium compound here, potassium ytterbium selenide, as well as some reports of the sodium ytterbium selenide, that it forms sort of kind of quasi-two-dimensional correlations under zero field. But for instance, the sulfide and the oxide is not, there's sort of certainly no reports that I'm aware of, at least, that they form actually quasi-two-dimensional order. It seems to be sort of an intrinsically disordered ground state. But these other systems actually seem to be very close to the same instability, if not actually in the same regime. So some of the stuff that we tried to do is then to instead look at a cerium 3+ ion. So now looking at the single electron case, trying to understand what types of magnetic ground states are realized in that regime. And so what we wanted to do is try and understand the impact of the anion, basically switching from going from tellurium all the way to oxygen, and how does that impact the magnetic ground state? So, in this previous slide, I showed you sort of these different studies of different anions, looking from the sulfide to the selenide and comparing with our, the previous work on the oxides. There seems to be some impact, so we wanted to understand this in the cerium compounds. And so we made the system rubidium, cerium, sort of oxygen, oxide, sulfide, selenide, and telluride. And we tried to first just understand how does the low temperature magnetic susceptibility evolve in these systems. And so it's kind of summarized here. So what you can find is actually kind of interesting. So when you look at the tellurium system, you can see as you cool down, you have this low temperature cusp and this magnetic susceptibility, suggesting either onset of some short range magnetic order or some type of freezing instability. And then as you go from the telluride to the selenide to the sulfide, this more or less stays the same. Perhaps the instability shifts a little bit in temperature, but not much. But then the oxide seems to be sort of qualitatively different. You can see the oxide is similar to the sodium ytterbium oxide, but there's really no sign of any freezing ordering transition. And as I'll show you on the next slide, we believe this is, the key thing that distinguishes the oxides from the others is that it generates a higher magnetic exchange field, which comes from basically closer R site spacing, which I'll show you here. And so if you look at, for instance, the cell parameters, as you go from the telluride to the oxide, you can see, of course, the cell volume decreases. But if you were to look at the oxygen basically parameterize a distortion of the oxygen octahedra, you find is that basically the trigonal distortion actually kind of leaps up dramatically as you go from the sulfide to the oxide. And you can see this also sort of in the magnetic susceptibilities, doing just a Curie-Weiss analysis. You can see that as this distortion changes, you go from, we know that the cerium distances from the oxide to the sulfide change from basically from 4.25 angstroms to about 3.69 angstroms. And you see this reflected in the Curie-Weiss field, right? So you go from basically the telluride, selenide, and sulfide, the Curie-Weiss is about -2, between, -2 and a -2.8 Kelvin. But then it sort of doubles as you go into the oxides. It goes to -5 Kelvin. So you have sort of much stronger exchange field in the system. And this is also borne out sort of in the isothermal magnetization, where if you just compare sort of at 2 Kelvin of the magnetization as a function of magnetic field, you can see all the other ones, basically oxide, the sulfide all the way through the telluride sort of collapse more or less onto each other, but the oxide, you can really see this stronger field, this stronger exchange manifest, even under 14 Tesla. Okay. And so, so that sort of suggests that the oxides are special. So one thing we were trying to look at was, how does the local electronic structure, or the configuration in terms of the crystal field, ground state change, across these systems. So looking at sodium ytterbium O2, there's been a number of different studies looking at these materials. So here's just some of our results, basically just using inelastic neutron scattering data to solve for the crystal field ground state. And what you get is that it's sort of a superposition of these, M1/2 and 5/2 and 7/2 states. And some key takeaways, in all of these systems, the crystal field modes are sharp, which are reflective of minimal, lattice disorder. So you don't have this substantial charge disorder in these systems, even though they sort of, we know that they're sort of forming these sort of quantum disordered ground states. And then I also mentioned that there are some hints, for instance, looking at the sodium ytterbium selenide. So it's a different level scheme because going from oxide to selenide, but in these studies, there's sort of hints of strong lattice coupling that were suggested by looking at a comparison, for instance, the thermal evolution of the inelastic neutron scattering spectra, as well as Raman scattering. And so we did this sort of similar type of analysis trying to look at the crystal field ground state of the cerium-based compounds. So this is again showing the same series of rubidium, cerium, telluride to oxide. And so what we find is actually something strange. So if you look at the crystal field spectrum of all of these cerium-based compounds, naively, it's a J5/2 system. You should only have 2 resolvable excitations out of that sort of, 2 resolvable intra-multiplet excitations out of that J5/2 manifold. But instead, across all of these systems, we always see 3. And so basically, you can kind of see these as these lines here, stretching, these horizontal lines stretching in the inelastic spectrum, and all 3 going from the telluride all the way to the oxide. And basically, you can quantify this by just taking a one-dimensional cut across these maps of scattering. And so, so it's most dramatic here if you look at the oxide cut here. As you go up here, these dashed lines mark the 3 magnetic excitations, these sort of flat modes that are consistent with these sort of single ion excitations or crystal field modes in these systems. What you find is that basically, as you change the anion site, basically the crystal field gets weaker. You can see these 3 modes all shift in, but they're always still there. And so I'll also just note here, right, if you just want to sort of illustrate the impact of anion disorder, or basically a disorder in the crystal field, you can look at some of these alloys amongst these. So you can look at the selenium sulfur alloy, or you can look at the tellurium selenium alloy, and you can see that all of these crystal field modes get much broadened. They sort of like bleed into each other, right? And so you can see that's really has a dramatic impact when you engineer intentionally chemical disorder into the system. So yeah, I don't have anything super satisfying, since there's a lot of people in the conference. This third mode remains a mystery to us. What we can do with work with Olivia Hozoi, basically, quantum chemistry predicts that the first 2 modes are the ones that one would expect for these systems, basically the excited states, and the third mode is a bit of a mystery. So we've sort of been trying to solve the crystal field ground states for this, assuming that the first 2 modes are the ones they were after. Sort of an unorthodox approach to it, and the third mode's a bit of a mystery. Our best approximation, our best understanding is it's some type of long-lived hybrid mode, likely due to the strong spin lattice coupling or yeah, the strong like electron phonon coupling in the system. Okay. I just want to mention briefly that we've also looked at the potassium cerium oxide variant. Okay, so this is, the previous slides I showed you the rubidium cerium oxide. So this is just changing the alkali cell site to potassium. And the ground state of that is actually different. It seems to magnetically order at 300 Kelvin. So these systems seem to be reasonably sensitive to perturbations, on the A site and also on the chalcogen site. But one thing we do see in the potassium cerium oxide that's common with the rubidium cerium oxide is we still see this third mode here in the crystal field spectrum. Here you can see it is outlined in blue around 170 millivolts. And here's just heat capacity as a function of temperature, showing that there's this ordering transition around 300 millikelvin in the system. And this is actually, the potassium cerium oxide sulfide selenide series seems to order. So for instance, potassium cerium sulfide has been purported to order around 400 millikelvin, similar to the oxide. And the selenide, there's not a lot of data actually above, below 400 millikelvin. So that's actually hard to say for sure, but my expectation is to probably show something similar. So it just really shows that, these systems are all fairly close to sort of this sort of intrinsic quantum disorder, but they sort of they're also, some of them are close to an instability where basically you can they seem to be induced to order with either changing kind of a steric effect by swapping out the A site or changing the ligand field by changing out the anion site. Okay. So another approach that we've been taking is to look at, instead of rare earth ions decorating the triangle lattice, we also want to look at transition metal ions. And so in particular, we want to look at transition metal ions where we can stabilize a J effective 1/2 Moth state. And so that's really, our approach has been to look at the ruthenium 3+ ion. So just as a quick review, right? So ruthenium 3+ is a 45 ion. If you put that into a cubic crystal field, and it acquires the low spin state, so basically if the crystal field is substantial enough, then you have sort of this low spin 2,2G electrons, and then you allow spin orbit to act on these, and basically you can split these 2,2G manifold into a lower J3/2 and upper J1/2 state, which is the J1/2 band is then half filled, and then you can allow the Coulomb interaction to act on it and to split that band into upper and lower Hubbard bands. And sort of what's special about this sort of J effective 1/2 state built from T2G orbitals is that you have this well-defined superposition of sort of T2G and spin states, T2G orbitals and spin states that that Kelly and Kelly Ewan showed a long time ago, I guess now, that if you were to decorate a triangular lattice or a network of edge sharing octahedra with these J effective 1/2 ground states, with these J effective 1/2 wave functions, that you can realize bond directional anisotropic exchange terms that mapped sort of the model of Kitaev, which was formulated for a honeycomb lattice. But in principle, on any edge sharing network, one can realize these terms. And if the conditions are just right, then Heisenberg exchange can be, basically if the crystal field's perfect enough and your lattice is perfect enough, then perhaps Heisenberg exchange could be canceled sufficiently to allow these Kitaev terms to dominate and stabilize a quantum spin liquid ground state. Okay, so of course this has been looked at in a number of different materials over the years. So this is here's two examples. So for instance, in the iridates, this is the same physics, but with iridium as the transition metal site. So sodium 2 iridium 03 or lithium 2 iridium 03. There are strong signs that these systems realize strong sort of Kitaev type exchange, and that's signaled via, for instance, anisotropic spin fluctuations above the Néel temperature of the system, although it orders below 18 Kelvin. Similarly, in like ruthenium trichloride, again, there's lots of signs from inelastic neutron scattering that Kitaev fluctuations are important in these systems, although it also seems to partially order below 7 Kelvin. And so the system we wanted to look at, before that, so why are these systems ordering? Just a quick review, the phase diagrams have worked out, basically you need to try and sufficiently cancel the Heisenberg exchange to land in the sort of quantum spin liquid regimes. And if Heisenberg is allowed to turn on in large enough extent via just distortions in the lattice, for instance, then you can be pushed to a number of different magnetically ordered ground states. And so similar phase diagrams have been proposed, not also for the triangular lattice, not the honeycomb lattice. And the triangular lattice is the one that we're focusing on. And in particular, we're looking at this system sodium ruthenium O2, which is similar to the sodium ytterbium O2 lattices I showed you before. So basically, you have a triangular lattice of ytterbium ions. Of ruthenium ions. It's late here. And between these, you have sodium ions, and the oxygen octahedra about the ruthenium ions are actually, it's fairly close to cubic. You have about a small 5-degree trigonal distortion. And so, so the first things we wanted to do when looking at this system, so this system had been synthesized originally by Chicano, but there was really no physical property measurements done on it. So first we wanted to see, okay, is this system indeed a Mott insulator? Is it an insulator? So here's just transport as a function of temperature, just showing you, okay, indeed it's an insulator. There's a charge gap in the system. It fits best to sort of variable range hopping. But nevertheless, the effective charge gap is fairly small if you were to kind of fit the high temperature transport to just sort of an Arrhenius-like activated behavior. It's maybe 100 millivolts or so. So it's a Mott state that's near some critical U over W ratio. So it's a weak Mott state. And that's sort of borne out also by some LDA plus spin orbit plus U calculations done by Ram Seshadri's group, where again, you can get LDA, you can get DFT to open up a charge gap if you include spin orbit and some on-site Coulomb interaction U. But I will just mention here that this is very kind of rough. I mean, this is very sensitive to the details of the structure. So that's consistent with, the system being very close to this Mott instability. Okay, so what's the magnetism look like in the system? So if you look at the magnetic state of the system, first I'll just say, we started off sort of with neutron scattering, going down to like 1.5 Kelvin. There's no signs of magnetic order and powder diffraction. If you go even lower to 50 millikelvin, again, there's really no signs of magnetic order within the resolution of powder diffraction for neutrons. If you look at the low temperature susceptibility, the susceptibility is actually best fit to with a large Pauli term. And so actually a fairly substantial, temperature independent Pauli term that's sort of on the order of like palladium metal, for instance. That Pauli term plus the sort of weak divergence, which can be captured more or less empirically by a 1% fraction of sort of spin 1/2 impurities. So that would account for the sort of weak divergence here. And then as you go to very low temperatures, so below about 1.5 Kelvin, there's sort of a weak cusp that forms. And it's sort of suggestive of a weak or a partial freezing of the magnetic moments in the system below this temperature scale. And if you look at the heat capacity of the system, this is low temperature heat capacity as a function of temperature. You can see the black line here. This is the zero field heat capacity. And you can see this sort of, again, a weak peak at about 1.5 Kelvin coinciding with this peak in the AC susceptibility. And then if you apply magnetic field, you can kind of shift this peak around. You can kind of push it up to higher temperatures. And so, but this, but the heat capacity, this weak peak seems to mark a threshold, or like a crossover, at least in the low temperature heat capacity of the system. And I can kind of illustrate that here. So if you were to look below that peak, so, and if you were to apply a reasonably high magnetic field, say 14 Tesla, to try and shift that peak away, so you can actually look at the intrinsic low temperature heat capacity. Again, so it moves to sort of a kind of roughly T² behavior at low temperature. But if you look if you're to look above the peak, then so this is basically above 3 Kelvin or so. One sees that the C over T versus T² fits to kind of this nice sort of Sommerfeld type model. So basically, one has a linear term in the heat capacity. And this linear term is actually fairly substantial. It's about 14 millijoules per mole per Kelvin. And it's field dependent. So as you apply a magnetic field, you can basically move this all the way up to about 17. And so there seems to be a crossover in the low temperature heat capacity as you cross this sort of weak freezing transition at 1.5 Kelvin, and you go from sort of a linear heat capacity, suggestive, even though that there's sort of a charge gap in the system. So it's something akin to like a metallic term in the heat capacity. to sort of this low temperature power law T squared. Okay, so what's happening sort of in the low frequency spin dynamics as you cool the system down? So this is some USR data collected by Mike Graff's group at Boston College. And basically, I want to show you here is that, as you cool the system down, what they find is that you can see these sort of low frequency spin fluctuations sort of freeze into the window of the muon spectrometer below about 6 Kelvin. And then by the time you get to 1.5 Kelvin, you approach this this weak freezing transition. What they find is you find this rather, kind of rapid depolarization that's captured via this this functional form, which is this called Gaussian-Prodden Gaussian function, which is then has to be dressed by some slow fluctuations. And so this Gaussian-Prodden Gaussian function is basically it's a Gaussian-Prodden. So basically, it's this Kubo-Toyabe function that's been further Gaussian broadened. Okay, and so this functional form's been used, for instance, capturing low frequency spin dynamics in like ytterbium titanate before, but others, for instance, another frustrated system, sodium 4-rubidium-308, which is this hyper Kagame system. The depolarization is also captured by the same form at low temperatures as you basically enter a freezing transition in that system. So one distinction between the system these two materials actually is the sodium ruthenate. When you apply a longitudinal magnetic field in the USR experiment, is that actually you don't fully lift this freezing, right? So basically, this depolarization is primarily dynamic, which is a distinction from the sodium 4-rubidium-308, where basically you apply a fairly weak longitudinal field and you can completely lift this sort of depolarization. Okay, so if you instead look at a bit higher frequencies and look at inelastic neutron scattering measurements, I probably won't go into too much detail on this due to time, but I'm happy to answer questions later. This takeaway is that there's sort of gapless continuum excitations. It has a fairly large bandwidth, about 35 millivolts. And it's very broad and diffuse scattering, which is actually fairly temperature independent. So basically, if you were just to look at a low momentum cut across the sort of broad continuum at 1.8 Kelvin, you can see there's sort of this broad sort of characteristic energy scale that appears here around 22 millivolts or so. And if you warm to 300 Kelvin, it still seems to be there. It's just sort of damped a bit. If you look at even lower frequencies and at lower temperatures, for instance, this is just showing you inelastic neutron scattering data, again, integrating a bit of this broadish continuum. And on the neutron energy loss side, so the positive energy side, you can see this is the part that's more or less temperature independent. And on the energy gain side, this bit is a bit for experts, just proving to you that as you heat the system up, these excitations obey detailed balance, basically, just proving that this temperature independent side is indeed magnetic excitations. And our current read of this suggests that you're sort of in the proximity of a magnetic quantum critical point. And if I were to just trying to integrate all the data together, the system behaves a bit like it's a nearly ferromagnetic metal, but it has a charge gap. And so some of the other things we can do is we can try and tune the chemistry of this system. So we've done quite a lot. Yes.
Hello. Yeah, you're almost out of time.
Oh, thank you. Okay, I'll finish. I think my last slide.
Okay.
Anyway, this is just to say that we can control a solid solution of these systems. Basically, we can engineer sodium defects into the ruthenium plane and basically induce an irreversibility in the magnetization and spin freezing. That's all. Basically, we can sort of lift the frustration by putting in-plane defects intentionally into the material. And then finally, so a lot of this phenomenology is similar to what's been seen in organic triangular lattice spin liquid systems. With the exception of if you were to calculate the Wilson ratio for the sodium ruthenium O2 system, it's large. It's about 8. It's substantially larger than this what's been reported in the organic spin liquid candidates. This is likely due to the impact of enhanced spin orbit coupling. And with that, I'll just summarize very briefly. So we think that these sort of triangular lattice antiferromagnets that are decorated with these sort of spin orbit entangled wave functions are able to stabilize quantum disorder in a number of different ways. And so some of the interesting regimes that we think are these sort of large gap insulators, which are close to the Heisenberg limit with S effective 1/2 ground states and rare earth moments. And those are sort of easily tunable magnetic phase diagrams. And I think there's a lot of work left to be done in those systems. And then the other regime that we've been trying to push recently is trying to look at spin orbit mod insulators with J effective 1/2 ground states on a triangular lattice, where you can have interesting things like extended exchange effects, anisotropic exchange terms, and also much larger energy scales. And so, yeah, so there's lots of interesting work to be done. And with that, I'll thank you very much for your attention, and I'll leave up the list of people who did all the work, which all the students here over a number of years are listed here. Thanks very much.
A nice talk. And the talk is now open for questions. So all the way, is there a mic there? Yeah, thanks.
Hello. Hi, Steve. This is Andre speaking. Thank you very much for your talk. I have a question about your measurements in the field. I understand that for the terbium system, so you're describing it in terms of an effective spin a half, yeah, so pseudo spin a half, which must be very anisotropic. And in this case, I don't quite understand what is an experiment on a powder sample in a magnetic field. What does it even mean? And how can you draw a phase diagram and a sharp phase boundary when the field is applied in all directions at once? Could you please elaborate on that?
Yeah, that's right. So I would say, yeah, so the phase diagram for that I showed for the sodium ytterbium O2, indeed, that's sort of like an empirical phase boundary that we sort of mapped with a field applied across a powder. So it's a powder averaged phase diagram, I suppose, where we see the phase boundary. But I will say, for some reason, the phase boundary that we see is reasonably sharp, meaning like within the resolution of the neutron scattering measurements, that phase boundary seems to be, reasonably well defined. But I mean, absolutely, yeah, people have done single crystal measurements on the sodium ytterbium selenide. And yeah, there's a strong anisotropy in terms of like, basically the instability is driven via the in-plane field primarily. There's no single crystals of the oxides available yet. So that's sort of why we're still sort of forced to show this kind of empirical phase diagram at the moment.
More questions? Yeah, go ahead.
Hello.
Hi.
Thank you very much for this nice overview of this triangular lattice systems with effective spin on half ground state. So my question is related to this cerium compound that you were showing, in particular the inelastic Newton scattering results with 3 crystal electric field excitations instead of 2 that one would expect for this ion. And you said the interpretation, if I got it correctly, is that you have some kind of long-lived hybrid mode, right? My question is, how far is the next spin orbit entangled state, the J7.5 state? Did you measure the higher temperature? Energies?
So, yes. So the J7 halves is up at 250 millivolts. Yeah. So we can see that. So this extra mode is distinct from going to the next multiplet. Yeah.
Okay, I see. Thanks.
Could you?
Hi, Steve. Thanks for the nice talk. My question is related to the ytterbium compound, where you see a quantum disorder ground state. So, I mean, almost all the spin half systems, or even classical spins on triangular lattice, show a 120-degree ground state, but you have found something very unusual, which is a quantum disordered ground state. My question is the up-up-down state also somewhat unusual? I mean, do you see a magnetization plateau which extends over a finite field range?
Yeah, that's a great question. So we, so we don't have low temperature magnetization data. Unfortunately, we just have low temperature susceptibility. But you know, from this data, it should be there. So this is, you know, chi versus H, right? So there should be a well-defined, you know, magnetization plateau here. But we don't have data, you know, measuring magnetization with 300 millikelvin, unfortunately. Yeah. And again, going back to Andre's question, right? You know, one naively wants to do this with single crystals, you know, and putting the field in the plane.
That's right. Thanks.
Okay. Any questions from online participants? If not, let's thank Steve again for a wonderful talk. And let's move on to the next speaker.